But let's begin with a very, very lightning review of the last quarter of quantum mechanics. First of all, the whole story begins by asking, how do you represent the state of a system? We could go back a step and ask, what is a system? But I'll assume you know what a system is. And how do you represent the states of a system? In classical mechanics, the states of a system are represented as points in phase space. In quantum mechanics, they're represented by state vectors. The idea of a vector is not a vector like a pointer in space pointing in a certain direction in space. It's an abstract notion. You can add vectors. You can multiply them by constants. And the mathematical structure of a state vector is a mathematical vector in a vector space. The vector space is not three-dimensional, except in special cases. It could be any dimensional. So we represent states by state vectors, and the symbol for a state vector is Dirac's ket symbol, ket, K-E-T, which is the latter half of the term bracket, like bracket or bracket. Every state can be either represented by a ket vector or by a corresponding bra vector. Together, we often put them together to form a bracket, or a bracket. The bra vectors are in one-to-one correspondence with the ket vectors, and you should really think of them roughly as being the complex conjugates, in the same sense as complex conjugates of complex numbers. Complex numbers are ubiquitous in quantum mechanics, and so are complex vectors. So state vectors are represented by, or states are represented by state vectors. The state vectors, well, we could say a little bit more, but if I were to say the whole thing, of course, we would then go through the entire quarter, so I won't. In addition, there are observables, things that you measure. Measurables or observables. In classical mechanics, there are also observables. They're the things you measure. But we don't spend a lot of time talking about their mathematical structure. We just assume you know what I'm talking about when I say position of a particle is measurable, or momentum of a particle, or the energy of a particle, or whatever. In quantum mechanics, we have to be very precise what we mean by an observable. And observables are represented by linear Hermitian operators. I'll label them with, what are these? Let's see. These are Greek letters. What kind of letters are those? English? Roman? Latin? I don't know. By Latin,
It's capital alpha.
Yeah, it's true. It's capital alpha. Okay. But Latin letters are representing observables, and they are Hermitian operators that act on the vectors. Hermitian, for our purposes, translates or is the quantum mechanical equivalent of real. Real as in real or complex or imaginary. They are the real operators, which are equal to their own Hermitian conjugate. Every such operator in the space of states is called an observable, and presumably there is really a way to observe it. The eigenvalues and eigenvectors of these Hermitian operators play a special role. So let me just remind you, what is an eigenvalue and an eigenvector? If you have a Hermitian operator, you can search for vectors. Let's label the vector. Let's label it little a, or better yet, alpha, since we want to label it with a Greek index. Let's label it with an alpha, and A, being an operator, can act on alpha, and alpha is an eigenvector of A if the action of A is just to multiply the vector alpha by a number. In this case, I'll use a redundant notation, the same notation for the eigenvalue and the eigenvector. And this says that the eigenvalue, the eigenvector alpha, is an eigenvector of A with eigenvalue alpha. And the significance of that equation is that, first of all, the set of eigenvalues of an operator or of an observable are the set of possible results of measurement. If you have a quantity which, when you measure it, can take on the value 1, 3, and 7, then the eigenvalues of that operator are 1, 3, and 7, and so forth. The eigenvectors are the state vectors of the system for which, if you make a measurement, the answer is definite, not statistical, determined, deterministic, and the answer to the measurement is alpha. Okay, so I assume you all remember this. I'm doing this mostly to just refresh your memory. Okay. Now, the particular systems we're going to be discussing mostly in this quarter are systems of particles. Particles are largely characterized by saying they're things which have a location in space, an ordinary location in space. For example, if space is one-dimensional, then a particle is a thing which has a coordinate x. It's located somewhere as an x. If space is three-dimensional, then particles move around. They have x, y, and z, and so forth. Let's write formulas for the case of one dimension, but I'll tell you what to do for 3 dimensions in a moment. Okay. Oh, sorry, let's come back. One point that I need to emphasize. For every bra and every ket, let's call the bra, let's call it phi. It is not necessarily the particular bra that goes together with psi, with the ket psi. For every pair like that, there is an inner product. There is a number. That number is in general a complex number, and it is represented as the inner product, and it's a number. It's a number for every pair of vectors. It represents a kind of product of the two vectors. It's similar in its mathematical structure to the dot product between two vectors in ordinary space, but it's a more abstract object. It's the inner product between two vectors, and it plays an important role in the logic of quantum mechanics. In particular, if two states are distinguishable uniquely by the property that there's some observable that you could measure which would be different in the two of them. Let's suppose there's some quantity that you could measure, and it is definite that the answer in the state psi is different than the state phi. Then we would say those two states are distinctly different. There's no chance of confusing them. There's a measurement you could do to distinguish them. Then those states are said to be orthogonal. Orthogonal means physically identifiably different, and mathematically, it's the statement that the two vectors have inner product equal to 0. So orthogonality is a fundamental property of relationships between vectors which says that they are different. You can't confuse them. Well, you can confuse them, but you shouldn't confuse them. Okay. Now, when it comes to particles, the most important observable is the position of a particle. And so let's just discuss particles moving on a line. The line is the x-axis. The location of the particle is just a value of x, and obviously x should be thought of as an observable. Okay. In particular, there are states which are labeled by a value of position. Let's call it x0. This is the point x0 over here. I'm just using the naught here to indicate a particular position. There are states which are labeled by x0, which have the property that if you measure the particle's position, you will definitely find it at x naught. Okay? Good. The next concept, oh, and of course, state vectors for different values, let's call them x and x prime. If x and x prime are two different positions, x and x prime, then clearly those two states are distinguishable operationally, and by measurement they're distinguishable, so these two states are orthogonal. Now, take any state whatever of this particle, call it psi, its inner product with the state representing the particle at x is called the wave function. The wave function of the particle, and it's written as psi of x. It's the psi that goes into the Schrodinger equation. It's Schrodinger's psi. I believe that Schrodinger was the first one to call it psi, PSI. And the meaning of the wave function is closely related to, but not the same, as the probability that the particle is at position x. Psi of x is an arbitrary function. Well, it's not completely arbitrary, but let's say it's some function. What does it represent, psi of x? Psi of x is closely related to the probability to find the particle at position x, but it's not quite that. The probability itself, let's call it P of x, is the product of the wave function times its complex conjugate. The wave function times its complex conjugate is positive. Any number, any complex number times its own conjugate is always positive. Probabilities are always positive. Psi of x's are generally complex numbers. They can be positive, they can be negative, they can be imaginary, they can be whatever you like. So it would not make sense to say that psi is a probability, but it does make sense to say psi times psi star is a probability. Good, all right, that's the most important property of a particle, that it has a position. It has eigenvectors which represent particles of known position. And we can construct, of course, a position operator. A position operator just multiplies psi of x by x itself, by x. All right, so that's the idea of position. The other important observable for a particle, there are many, of course, there are many observables for a particle, but the other particularly important one is called the what? The momentum. The momentum. In classical mechanics and in quantum mechanics, positions and momenta come together. Oh, before we do that, I should discuss the issue of a particle moving not just in one dimension. What happens if a particle is moving in 3 dimensions? In other words, like a real particle. Then it has 3 observable positions, the 3 components of its position, namely x, y, and z, if you like. But since you can rotate axes, you can just think of the position as a point in 3-dimensional space. In that case, we would just think of x here as a point in 3-dimensional space. We could fill it out. We could fill out the equations by saying there are states which represent particles at known locations in 3 dimensions, x, y, and z. This represents a particle located at a point in 3-dimensional space, over here, x, y, and z, and the rules would be similar, very similar. The inner products of x prime, y prime, z prime, that would be 0 if there's any mismatch, not if x is not equal to x prime and y is not equal to y, but if the entire point x, y, z is not the same as the point x prime, y prime, z prime, then these are observably different positions for a particle, and the states are orthogonal to each other. I'm going to suppress the y and z, but keep in mind that the position of a particle depends on the dimensionality of the space that we're talking about, and in the real world, space is three-dimensional. Okay, for each component of position, there is also a component of momentum. In classical physics, for non-relativistic classical physics, the momentum is just the mass times that component of the velocity. In quantum mechanics, the momentum is also observable and is also represented by an operator, by a Hermitian operator. Hermitian operators can be thought of in the abstract as objects which act on mathematical vectors, the space of states, or they can be thought of more concretely as operations on wave functions. Either one, you can think of them concretely as operations what about x itself? What is the operation that represents the operator x? Well, it's just taking the state vector, psi of x, or taking the wave function, and multiplying it by x. If psi of x is a function representing the probability amplitude, psi of x is called the probability amplitude, or the wave function of a particle, then if you want to apply the operator representing position to psi of x, you just multiply psi of x by x. That's all. The eigenvectors of x are the wave functions which are highly peaked, very, very narrow Dirac delta functions. All right, in the same way, the momentum operator, now I'm not going to explain this in detail. For this, you go back to the lecture notes or to the lectures themselves. What lecture was it that we talked about momentum? Anybody remember? Art?
Several of them, but I think around 8.
Around 8?
Maybe 8.
Yeah. 8 was, that's right. I remember with great grief, lecture 8, right? Okay. So the momentum of a particle is represented by an operator called P. And P also does something to psi of x. What it does to psi of x is it differentiates it. It differentiates it with respect to x, but not quite. The real thing is that it multiplies it by minus I, the complex number I. There's a factor of Planck's constant, h bar, and then it differentiates psi, d by dx, psi of x. That is the operator that acts on wave functions that represents the observable momentum. Everybody remember this? Yeah, we went through it. Okay, now, what about the eigenvectors of momentum? The eigenvectors of position are Dirac delta functions. They are functions which are zero everywheres except at the eigenvalue position. In other words, the eigenvector representing a particle known to be at x naught is a function which is zero everywhere except at x naught, where it's very high and very narrow. Let's not worry about its precise mathematical definition. It's called a Dirac delta function. And it's not too hard to believe that if the wave function of a particle is so concentrated at a particular point that the probability for finding it is zero everywhere except at that point. That, of course, makes sense. Now, what are the states for which the momentum is certain? In other words, what wave functions correspond to particles with definite momentum? And those are gotten by solving the eigenvalue equation. The eigenvalue equation is that P, whatever it is, in fact, we know what it is. Well, let's write the formal, let's write the abstract equation first, that P on psi is equal to little p naught times psi, the eigenvalue being little p naught. Little p naught is the value of momentum that this particle has, and in this particular state, the momentum of the particle is known to be p naught. This equation translates, just replacing p by minus I h bar d by dx, minus I h bar d psi by dx is equal to p naught, the number, a numerical number, times psi of x. Psi is a function of x, psi of x. And this is easy to solve. This is one of these equations which says that the derivative of something is proportional to that same thing. Derivative of psi, apart from a numerical number, the numerical number we could get rid of the I h bar on this side, it would reappear on this side. This is the equation of the type that represents an exponential. The derivative of something is proportional to the something itself, and the solution of it is e to the I p naught x divided by Planck's constant. Now, I often get very tired of writing Planck's constant, and I often just set it equal to 1. We'll sometimes do that. In fact, I'll try to track it for the time being, but later on I may just drop it. And I think by the time I do drop it, I will have done it enough times that you'll know where the right place where it goes.
Question?
Yeah.
In the two equations you just wrote there, the upper one with the cats, that would say that those are, or that's a eigenvector of the
Yeah,
moment.
that says that eigenvector, that psi is an eigenvector of p with eigenvalue p naught.
But the one below holds for any wave function, right?
You think any wave function is e to the I px?
No, but the equation before it.
Here?
The same holds for any wave function.
No, most wave functions don't satisfy this equation. No. In fact, it's true for basically this wave function. Okay. Now, you'll notice, of course, that there's a huge difference between the eigenvectors of position, which are these narrow little spiky functions, and the eigenvectors of momentum. In particular, let's take the probability that's associated with e to the I p naught x. That's multiply it by its own complex conjugate. What happens if you multiply this by its own complex conjugate? You get 1. E to the I something times e to the minus I something is just plain 1. So this wave function, the one which represents a particle with a definite momentum, its probability distribution is smeared out over the entire line. By complete contrast, the eigenvector of a particle located at a definite position is highly concentrated, infinitely narrow. And this, of course, is a manifestation of the uncertainty principle. If you know the momentum of a particle, then its position is completely uncertain. And likewise, if you know the position of a particle, its momentum is also completely uncertain. I'll refer you back to the lecture notes for that purpose.